is going to be a fun one. Dr. Winnicus warned me that the projector was cutting in and out. My laptop's recognizing the HDMI cable. It's recognizing it as a second monitor, and then just nothing shows up. So we're going to try to do this with the in-room PC, so this should be interesting. We'll start by answering a couple of these questions. If you fail the interview third time, is it automatic if you pass the quiz? I'm not 100% sure what the wording is getting at, but as Artemis says, you can use multiple recovery opportunities on the same thing. So if you fail a third opportunity, quiz or interview, you can use another recovery opportunity to get a fourth opportunity for that. I'm not sure what passing the quiz means. Like if you pass the quiz, you don't automatically pass the interview, if that's what you're asking. But you don't automatically fail the class either, depending on your complete situation. All right, so luckily everything's on here for the most part, but I gotta get used to all this software on this. Oh my goodness, I can't even use the mouse right. So let's go to LO4. And I want to go back. There were some slides that we missed in the past few lectures, so I want to clean those up first. And then I have not used Acrobat Reader in forever. And then the tough part is that I got to go. It's a Friday. I got to go over some test cases. I might be doing that in Notepad++. So we'll see how that goes. Full screen mode, I guess, would be the best here. Okay, cool. Oh my fucking God. All right, but we'll do this. All right, so I want to review adding and removing a node just very briefly, but this is where we'll pick up, and I'll just clean up these slides. So adding an element, we can adding and removing isn't difficult in a linked list. The idea of a linked list is that operations like this are easy. Since these nodes are all over memory, we ask for more memory, put a node there, and then update the references, these next references, to be able to add that element to a list. So we want to add the value 2 after the value 3. We need a reference to 3 because we have to update this node, and we're going to add our new node with a next point referring to whatever this node used to be referring to, and this node's next will be updated to the new node that we just created. And in code, we saw that it looked like this. We could get it done in one line. So from the node before the position that we want to insert the element, we're going to say this next is equal to a new linked list node with the element that we're adding, and that linked list node is equal to the next node from that linked list is equal to whatever the next was going to be. We replace that next over here. So next is one value here and a different value here, just like what we saw in the prepend when we were doing it in the memory diagrams, just a little bit different context here. Yeah.
Out of curiosity, so if you were wanting to, you didn't go over this, but like for instance, soon you're going to be talking about removing it, right? Now,
talk about what?
Removing an element.
Here.
Removing an element, right?
Yep. Yeah, that'll be the next few slides.
What if you wanted to remove like every other element?
Every other element?
Yeah.
It'd be a good homework question, I guess. If I wanted to remove, not this semester.
I'm just kidding. It doesn't have to be like a homework question.
But that would be, I'll say this way, it would be a good interview question. Like if an interviewee asked you that, not in this class, mind you, but out there like interviewing for an internship or something, it'd be a little too advanced for this class.
Oh, it is? Okay.
I mean, not overly so, but if we're trying to find the line of passing the interview or failing the interview, it'd be a good one. Like if you're knocking the interview out, we'd ask you as a challenge question. If we had like AOs on the interviews, we'd ask you something like that. If we wanted to do that, I would iterate over the linked list. Ooh. Can't touch my keyboard there. I would update this next equal to the next, and then move one node forward and just keep repeating that process.
Right.
Is how I would do that.
Because like the reason I ask is because I was going over this and I understand that like if I wanted to get to 4 to 2, right, I would do 2 next, 2 arrow next equals 2 arrow next, right? So what if I wanted to just iterate through every other one, but that's...
If to do every other, you would call next twice, but for specifically removing the node, you would just call next once. So.
Okay, all right.
Because you removed one of the nexts that you would have called.
Right.
So you don't have to call next twice anymore because you removed one of them.
Okay, all right. Thank you.
Some days this fan is on and it blows right next to me. I can't hear anything. I have to just move away from it. But I have to go over here to advance the slide. So, actually, do I? Now that I'm using the in room computer, I thought they usually had the things. So if we want to delete a node, a similar thing, we need a reference to the node before the node that we want to remove. So if I want to remove this node 2, I'm going to need a reference to this node before it. And from that node, I'm going to remove that, the node containing 2. And to do that, we update next to be the next's next. So whatever my next node refers to, I want my next to refer to that node. So we just completely cut that one node out of the list. We update one reference. That's it. That's all it takes to delete an element. We don't need more memory or anything. We just update one single reference, and that element's removed. Mind you, this is for a mutable list. We can't do these inserts or removes from an immutable list. That gets a lot trickier, a lot messier. We have to copy a lot of elements. For a mutable list, just update this one reference. Super easy, super fast operation. It's O of 1 operation, assuming you have a reference to this node already. It might take O of n time to get to this node to get that reference, but once you have that reference, O of 1 to remove. You're just literally updating next. Next equals next.next. That's it. Very simple to remove an element from a linked list. Just update the links. And this node still exists. It's still there in memory. We just don't care about it anymore in this specific list. Someone else might have a reference to that node, and they'll have the list 2.1, and that's fine. They can still have that list. But this list that we're looking at here doesn't contain that node anymore. All right, now let's get to some new stuff that we didn't get to. Say we want to find an element in a list. I have some specific element that I want to find based on the equal operator. I want to know if an element is equal to this one. Whatever it is, it's some type A. It might be ints, it might be strings, it might be characters, it might be vectors. I don't know what it is. But I'm going to assume it has an equal method that's not just comparing references. Or even if it is, maybe that's the use case of whoever's calling our find method. That's fine too. But I want to find this element. So I have a linked list. I have a reference to the head of the linked list. And I want to say, does this list contain this value anywhere in the list? If it does, return the node of where we found that element. If it doesn't contain it, return null. So I want the node. I don't just want the value. I want the node because, in practice, this might be called to find where I want to insert a specific element. So I get a reference to the node, and then I can call my insert or my delete methods after that. Our methods depend on having a reference to a node, so we're going to return a reference to that node. So to do this, I have two base cases, which I think this is the first example I've had with two base cases. I mentioned it once very briefly, and I heard at least one of you had a question on an interview, I think, if you can have two base cases. If you fail an interview based on something like that I only very briefly mentioned in lecture, let me know. I can take a look. And if that was a borderline decision, that's the only reason you failed the interview, I'll give you credit for that one. So just throwing that out there. But we have two base cases here. If we find the element we're looking for, I know that this node has that element that I'm looking for, and I can return that node. And reminder, this is defined in the linked list node class. So this is a reference to a linked list node. If that linked list node has the value we're looking for, return that node. And for what it's worth, this will return the first reference. If this what we're looking for is multiple times in that list, it will return the first node containing it. If we're at the end of the list, return null. Is this broken? This isn't broken code, is it? This dot value equals, oh, geez, yeah, no, it isn't. If we're at the end of the list, Like I definitely tested this and stuff. All right, so if we're at the end of the list, return null. If we get to this check, this conditional, it means we already checked this dot value and it wasn't the element we're looking for. So if this dot value isn't what we're looking for and we're at the end of the list, return null. So those are our two base cases. Either we found the element we're looking for or we didn't find the element we're looking for and we've reached the end of the list. Then return null. This element is not in the list. Else, recurse. Go to the next node in the list and call the same method. If I don't contain the method that I'm looking for and there is a next node, I'm going to say, hey, next node, do you have the element we're looking for? Then it's going to keep asking all the way down the chain until we either reach the end of the list or the element we're looking for. Then either return the node containing that value or return null all the way up the recursion. And I do want to start, well, not start. I want at least one slide. This is the only time I do this, is compare the recursive method to the iterative method. We can have debates for days, months, years about this. I think the recursive method is a little bit cleaner here. I think it's cleaner code if you're getting to the point where you're used to reading recursion. Once you get to the recursive part, it's like, oh, wait, what's going on here? Until you get used to that. But there is a debate to be had. Like the iterative method of doing this isn't that complex either. We're going to initially look at the first node. So this is called on the head of the list. So node is going to be the head of the list. And then while we're not at the end, the head of the list, the first element, and as long as we're not at the end of the list, as long as we haven't gone off the edge of the list, check if we're looking at the value we need to find. If we did, return it. Otherwise, advance to the next node and start the loop over again. So keep checking every single node's value if it's the value to find. And if we never hit this return statement, then return null. Because we made it to the end of the loop without returning, we're going to return null, which is a little icky for Scala developers. We got that return in the middle. We don't like using the keyword return in Scala. We can rewrite this without that, but it gets a little messier, a little trickier. So the return does clean up a little bit, to make a fair comparison to the recursive method. Getting rid of this takes just a little bit more effort, a little bit more code, because we still want to return the first instance. If we could return the last instance, then sure, we just update node. We still actually have to have extra code. It would still be a mess. There's no super clean way to do that. But with the recursive method, there's not much logic going on here. We have the same logic here and here, but it's I don't know. I don't want to debate over it. But I think the find is a little cleaner. But it's close. Is my point. It's close. When you're looking at these two, you would probably think I'll stick with this and not have to learn a new complex topic. It's close enough that you're going to say that. When we get to trees, hopefully I can convince you that that's no longer the case, that's going to be a lot more complex to do the iterative method. Is reversing a list expensive? Yes and no. It's O of n, but to reverse an entire list, no matter what data structure we have, if we want to reverse it, we would expect it to be O of n. There's just no getting around that. If you have to move all of the elements, it's expensive in an array, it's expensive in a list. You could kind of make it not expensive in a doubly linked list, but I would expect it reversing to be expensive with any data structure, unless you build a data structure specifically designed for reversing. But any out-of-the-box data structures, it's going to be expensive. Your interviewer asked you about minimum and maximum number of base cases. Oh, in this class. Yeah. What's the answer? What's the minimum number of base cases you need? One. You can't have 0 or else you're going to have infinite recursion. What's the maximum number of base cases? Infinity. Yeah, there's really no limit to number of base cases. So it's a little unfair because I didn't really talk about multiple base cases. So if Bach is saying if you got asked that and you failed the interview and that was the borderline decision, definitely let me know, because I wanna fix that. Because I really didn't talk about maximum number of base cases, multiple base cases. I always only showed one base case. So yeah, that's not super fair. Is there a speed difference between the two methods? In this case, not an asymptotic speed difference. There's no asymptotic difference. They're both O of n. And that'll be the case. Like you can rewrite these, any recursion that I'm showing, you can rewrite using a loop, and it shouldn't affect the runtime, asymptotically anyway. The same will be true with trees. Like it's just making our lives easier in terms of coding. Yeah, you're going to say infinity, but then thought of the lecture examples and said 1. Yeah, definitely in that situation, because that's not exactly fair. So when grades come out, we can talk about that. Hopefully you just passed the interview anyway. I'll tell the TAs, I think I already did tell them about this too. Like that's not fair because I didn't really cover it in my lectures. Where Paul did several examples with multiple base cases, which is why it was on the interview to begin with. And I just didn't catch it to veto that question in time. So if that is a situation, there was another one too. I was just talking to my TAs about. I guess that was an LO2 thing. If you're asked like what's passed by reference, I don't think that's a fair question either, because we talked about pass by reference for like a week or so, or weeks, several weeks. We talked about it all the time, but I very rarely use that phrase. I didn't call it pass by reference. But whenever you're calling a method and giving it a reference, we call it pass by reference. But since we didn't use the vocab and Paul didn't say it a single time, so that was an unfair question. But as long as you could understand the concept, it was fine. So if anybody lost points for that, lost interview credit for that one too, we can talk about those. We can negotiate those. Anything where it's like, I answered this because that's what you taught me, and then the TA said it was wrong. Like any of those things are negotiable. All right, so let's talk about a few first order, using functions. If you look in the examples repo, there's all kinds of these. I'll talk about a couple of them just to show you like how these things work under the hood. With Scala lists, we had a whole bunch of methods. I spent a whole lecture just rapid fire. Here's map, here's reduce, here's fold, here's I'm blanking on the yield, I guess. We did all kinds of these. I'll just highlight 2 of them, for each and map. For each, here's a function, call it on every node. If we want to do that with our linked list node, this will be called on the head of the list. We're going to take this function, call it on its value, and then as long as we're not at the end of the list, call it on the next node. So you're going to, hey, call this function on every node in this linked list. Each node calls the function, and as long as we're not at the end of the list, hey, next node, you got to call this function. So we still have recursion here, except we only have, I guess I don't show the base case. The base case is next equal null, which would be in the else, which just doesn't do anything. The base case does nothing after calling the function, I suppose. And then the recursive step is just calling it on the next element. If we're calling it on the next element and the base case is the end element of the list, we're eventually going to get to the end of the list, unless another nice interview question for recruiters. Unless we have a circular linked list where the last element in the list refers to the first element. I briefly mentioned this last time. Then you have a circularly linked list, and then the recursion goes on infinitely. Actually, I like that for a question for 116 as well. Your TAs might ask you that one, actually. You should be able to get that one just by your understanding. If you understand how a linked list works with the next, and there's never a null, you should be able to put that one together. That's going to go infinite. And map. So let's talk about one more. Here's a function. Call this function on all your elements and give me the return values in a new list. So for Scala lists, we would create a list. We would call map with some function. This one just squares all the elements. That gives me a new list with all the values squared, and then that list contains what we expect it to contain. So we've used this plenty of times. We used it a lot in homework 3. how does this work on our actual linked list? How could we implement this? So I want a method that's taking a function and then returning a new linked list with all the values after that function is applied. For this, first, just like for each, I'm going to call the function first on the value for this node. So the first, this is going to be called first on the head node, the first node of the list. Call the function, get that new value that we're going to return in the new list. If we've reached the end of the list, if there's no next node, return a new linked list node with that new value and next of null. So here's the new last element of this list. And then as we return up the recursion, we're effectively prepending linked list nodes with the new value for that node, and next equal to the recursive call to the next node. So each node is going to get this function called on its element, and then create a new node that's a copy of itself, but with the new value, and then link all these chains together. So as the base case returns, we're returning a new linked list node that refers to null, the new last node. That's going to return to the second to last element. This becomes this single element, and then create a new node with that value referring to the next one. Return that to the third to last element. That's going to go here, a reference to the second to last. Third to last adds its value, creates a new node to wrap around that, and then return that. Then keep returning up until the head of the list. And the head of the list will have it return a node that refers to all of the rest of the list. So we can map and get a whole new linked list node, that is the head of a list with all the new elements that we expect, which is the same thing that Scala's map function is doing. This is a little beyond the scope of what we really need to know, but just for the curious, we can call map and change the data types. So like here, my function takes an A and returns an A. If I have a map of ints, I can return a map of ints. But we know that we can change values. We did this in homework 3 several times. We would take a list of T's and change it to a list of doubles, and take a list of doubles and return a list of T's like we do for the application objective. Not necessarily, since I mentioned, I better finish that explanation. You don't necessarily want to change them. I've been given this hint in office hours. I might as well give it to everybody. In the application objective for homework 3, it's meant to parallel something you've learned in top K, where top K, you have a list of T, and the trick for that one was you can't ever just convert it to a list of doubles and work in doubles, because you can't go from doubles back to T's to return the list of T that you want to. So what you were expected to do is write a comparator that's going to compare T's, and that comparator is going to call the function to be able to compare by the values after the function is called, and then compare doubles, but still sort a list of T, but the comparator converts to doubles, so the list never changes to doubles. So you learn that in top K is the same lesson that we're applying in the genetic algorithm in the AO, is you have a list of lists of doubles, and you want to keep that as a list of doubles. You don't want to convert that to a list of T using that incubator. You want to sort your list of doubles using the incubator and the cost function without ever converting them to type T. So that was the idea there. So same thing here. We don't necessarily want to use map for the homework, at least not in top K, not in genetic algorithm. But if we did want to change the types here, we're going to take a function that takes in an A, that's the type of our list, and returns a B, which is going to be a new type parameter that this method takes. So we have a type parameter for the class. When we create a linked list node, that takes a type parameter. But we can also take a second type parameter that's different from that one in our methods, and our method can take a type parameter. So I take a type parameter here. I already have a type parameter A defined for the linked list node class. Take a function that converts A's to B's and return a linked list node of B. And all the code is the same. Same for this. So this is how map can change the type of a list by taking another type parameter instead of just converting from the type of the list to the type of the list. So that's how that worked. For the curious, I want to make sure that's out there. So it's not like, wait, map is more powerful than what you showed us. How does it do that? That's how it does it. What are circular linked lists useful for? There are some like edge case uses out there, but in general, they're not useful. It's usually if you made a coding error, if you've made a mistake and looped your linked list onto itself. It's usually a bad thing. But there are certain cases where it can be used, but they're far and few between. If you applied a recursive call on a circular linked list, would you get a Stack Overflow? It depends if your recursion is tail recursive or not. In general, you get a Stack Overflow, though. But if it happens to be tail recursive, it'll be the same as an infinite loop. It'll just run forever. Your program will hang, and you won't know what's going on until you investigate. It'll just sit there and think forever and burn up your CPU. So in some sense, it's better to get the Stack Overflow, because at least then you know what the problem is. But if you're tail recursive, you'll just burn up your CPU. What do we call the A being used to get the linked list nodes? Just a type parameter? Yeah, that's a type parameter. So this is in the linked list node class, and somewhere up here omitted on the slide would be class linked list node of A, and then the parameter list. So that's omitted on this slide, which should be, bless you, right here. So linked list node takes the A, and then inside this class, we're adding all of these methods that we're talking about: the remove, the delete, or the add, insert, delete, find, map, for each. All those go inside of this class. So inside this class, we have a method map that takes a second type parameter B. So that's how we can change a list of node A and then map it to a list of node of type B. But yeah, it's anything you want it to be. Doesn't an infinite loop create a Stack Overflow? No. No, the Stack Overflow comes from constantly putting stack frames on the stack, and your loop isn't going to be able to add new frames to the stack. You can call a method inside of your loop, but to continue on with the loop, that method has to return where the stack frame would be destroyed, and then you go on with the loop and put one stack frame at a time there. So you don't have the same issue with your loops. All right, that took way longer than I thought. Let's keep moving. Stacks and queues were cool. We left off around here for the memory diagram. So we went through the constructors. We prepended 3 times, and we have a linked list. My list stores a reference to a linked list. A reference to a linked list is only a reference to the first element or the head of the linked list. So we refer to 480. 480 refers to 200. 200 refers to 350. 350 returns to null with this silly syntax of grounding the thing. So if I have mylist.next.next.value, which is the same as mylist of 2, or mylist.apply of 2, mylist.next.next.value, I'm going to get the value 1 and print 1 to the screen. All right, now let's get to some recursion. Let's get another example of recursion out there. I want to call mylist.size and return it to a variable list size. And my list stores the reference 480. So this of the size method is 480, and size doesn't take any parameters, so only takes a reference. This, which is the object which called the method. Size does nothing, but it has a helper method that's going to do stuff. And I'm going to initialize that call, call the helper method with an initial value, which is going to have use tail recursion. But I'm not going to collapse the stack frames. Even if on any quiz you get a tail recursive method, still draw out all the stack frames, because we're interested in knowing what goes on with these things. I'm not going to collapse the stack frames. I'm drawing every one here, even though technically they would be collapsed because it's tail recursive. Then I'm going to call this helper with an initial size of 0. Size is my accumulator variable. I knew that wasn't going to work. Size is my accumulator variable. So I'm going to accumulate the size as I go down the recursion. I'm going to add 1 each time I visit a node. And then my base case is to just return the total size, which is size plus 1, because I want to count that node. So we expect this to be 3. Let's see if the recursion works for us. The recursion immediately calls size tail rec. I should have my this dot. I've been pretty consistent with that, and I forgot it here. This dot. So this is still 480. Size is initialized to 0. And we start some recursion. So we're going to hit, we're not going to hit the base case. This is 480. Its next is not null. So we're going to hit our else, this, and call this dot next dot size plus of size plus 1. So 0 plus 1, we're going to get 1, and now this is 200 because that was the calling reference. This dot next up here, this dot next is the calling reference, which is 200, which is this linked list node. So this is now 200, and size was incremented. We still haven't hit the base case. So in this stack frame, we're going to say this dot next, make the recursive call with 2. So this dot next is this linked list node. So this linked list node is calling with 2 as its parameter, 1 plus 1. And then this, in this stack frame, we have 350. This dot next does equal null, so we finally hit our base case of the recursion. And this node is going to return size plus 1. Size is 2, so we're going to return 3 all the way up the recursion. And each stack frame has nothing to do but just return. This is where tail recursion would collapse all 3 of these calls into one stack frame because there's nothing left for these. These 2 stack frames are just dead weight at this point. Their only purpose in life is to get the return value here and just return it all the way up the recursion. So those would be removed in tail recursion. So we reach our base case, return 3 all the way up the recursion. Size, technically not a recursive call. It gets 3 and just returns it anyway, though. And then list size gets 3, and we print 3 to the screen. Any questions about that? I think it's nothing entirely new, but it's just reinforcing some stuff we've seen. We get recursion, but with linked lists, a bunch of reference stuff going on. It says LL node. This example should say LL node. Just for the memory diagram, oh, it says LL none. Yes, it does. Oh, I didn't update that, did I? Yeah, this should say LL node. But I have like 18 slides with that on there, and I said, oh, I don't want to do that. And then I forgot. I'll try to remember and update it. One typo, but it got cut and pasted like 80 times. Okay, any questions on this? We feeling good about recursion and references and all that stuff? We should be. Since we're at the other side of the LO3 quiz, I would assume. We're doing pretty good with all that. All right, so now the trickier part. Let's try, and I can't run it. I'm going to try the laptop just one time, because, yeah, I can't even run the code. Frustrating. All right, so let's go to some code. Let's go to our tests. I guess I don't really have anything to talk about here, but let's copy this. And you can watch me struggle to write code without an ID. It's been so long. Let's get this. Let's collapse this. Let's go to task 1 and write a test for at least one of these things. Oh my goodness, can I even do this? I've become so dependent on IDs. Let's do it. Okay, let's write a test for locate players. So the idea here is, and for some of these, the testing is going to be more work than the code. We're fairly familiar with that concept now. For better or worse, it's kind of just a fact of programming that sometimes the tests take longer. For these tests, we need to create some linked lists and then use those linked lists to be able to call our methods. So the first one, locate player, is going to need a linked list of type player location and a string. So if I call locate player, well, let me set up the whole thing. So first, this is going to be a method of the AI player class. So I'm going to need a player object, which is going to equal a new AI player. And I need to give this player some ID. Why not player 1? So I need to create a player, and that's what the method's going to be called through. So eventually, I want to call player dot locate player of some string and some linked list node. I'm going to create this as a variable, which is going to be the player list, which is going to be a linked list node of player location, which will equal a new linked list node of some value. And I'm going to do this on multiple lines. Some value, which is going to be a player location. If we look at the player location class, it'll take an X and a Y location. I gotta find where it is now, the old-fashioned way. It's got to be in enemy AI player location. So it's going to take an X and a Y value and the player ID. And I would have went through more code. I'm not going to click through on GitHub. It's kind of a pain. But there's quite a bit of code provided on this project. Unfortunately, we did cut a few topics, or fortunately, depending on how you look at it, from 116. So you won't be able to understand all of this code. But all of the code that you need to write is going to be in this AI player class. So this is the only class where you're writing code. This is where you're writing all of your code for the project. So at the very least, I wanted to make sure your code was confined to one spot so you know where to write your code. But sometimes you do have to use classes that are defined elsewhere, and player location is one of them. So player location, it's an X, a Y, and a player ID. So let me give some 3.0, 4.0, and player 2. And the next can be null. And then I can start creating this list. List equals I can start prepending to this list. Oh, come on. Player 1. And I start prepending to this list. And 2 is fine for the example test case. And then give this the list and give it a player that I expect. So if I give this player 2, this is a player location. Now I want to assert that actual, one thing I want to make sure I assert actual dot, what was it called? Player ID. ID. For some reason, it's one of the hardest things in programming that's tripped me up so many times. ID, should it be capital D or lowercase d? I don't know. I always have to double check. Got to be very careful with that. Will equal player 2. And then compare doubles to check for the position 3.0, 4.0. Which I'm not gonna do all that. Then compare the doubles. And then do the same thing. Call locate player with player 1 and make sure you find that player and that everything is checking out and everything is what you expect it to be. And call it with That's not what I'm highlighting. Call it with the valid values in that list, and don't call it with either an empty list or with an input that's not in that list. So we are making some assumptions to make our lives a little bit easier here, which honestly could just be added to the assignment to check if it's not in there. But if it's not in there, well, your code can crash, it can break, it doesn't matter. And in your testing, don't give it a player that's not in that list. So it keeps our testing a little bit simpler. In homework 4, I like to back off a little bit. We're not going to hammer you on all the edge cases and go nuts with it. Just assume that it's in there. Closest player, very similar idea. You're going to set up a list of players and then compute the closest player by L2 distance or Euclidean distance. I feel like every time I say L2, everybody just looks at me like I'm crazy. I think that's something you don't really hear until upper level math. I should probably just stop using it. But Euclidean distance, square root of the sum of the squares. So give it a list of players and expect, given some player, if I want to find the closest player to this player, remember this is going to be referenced by the player you're calling it from. I'm calling it from this player. If I call closest player, it's whatever player is physically closest to that player is going to be the one that we want to be returned. And then compute path. I don't know if I'll write code for this, but I'll write some kind of pseudocode. So the first two test mostly the same way. But compute path is a little bit different. Compute path, you're going to call compute path. This needs to be called through a player because all of your code is in the AI player class. One byproduct of that is you need a reference to a player to do any of this stuff. So we're going to grab a player here, create a player. Oops. And call this compute path method with a start location and an end location that should return our linked list node of grid locations, which equals player dot compute path of some grid locations for our start and end of our path. So let's create a new line here. New grid location. Say I want to go from 2, and these are integers, to new grid location of 4. That's going to give me a path. And grid location is literally 2 ints, and it's the XY position on the game board. That's going to give me a path of linked list nodes, or a linked list of grid locations. And I want to make sure to do check if path starts with 2, check if path ends with 4. So we're in a situation, the trick with this one is we're in a situation where there's many correct answers. So we want to check if we start and end at the where we expect. Check that the length of the path is minimal. In this case, I can go from 2 to 2 3 to 2 4 to 4 3 to 4 4. Oh, and I lost track of 5, right? Path of length 5. I'm just not going to put a number in case I say the wrong one. And check if all moves are valid. So So you can only go up, down, left, or right. So when you're checking two adjacent grid locations, make sure that either X differs by 1 or Y differs by 1, and not both, no diagonal moves, to make sure that this is a valid path. So this gets a little bit tricky to check. It's one of those classic situations where there's no one correct answer. You should be getting used to that by now. There's no one correct answer. There are a lot of correct answers. So we're going to check for all of those correct answers in one way or another. All right, and have a great weekend. See everyone Monday.